In this short final video of this lecture, I'm going to go very briefly through some problems when we're doing machine learning and some solutions to them. So the first one that I want to address is multi-class classification. Although many classification problems can be defined using two classes, some are defined with more than two classes, which requires adaptation of our machine learning algorithms. In multi-class classifications, there could be like, I don't know, n number of classes, and the labels could be any of those n number of classes. Many machine learning algorithms are binary. For example, support vector machine is an example. Some algorithms can naturally be extended to handle multi-class problems, like the decision trees. They could simply be changed to adapt to multi-class problems. Logistic regression can also be naturally extended to multi-class learning problems by replacing the sigmoid function with a softmax. That is also true for KNN algorithms. This is a straightforward to extend it to multi-class classification. Basically, when we find a k closest example for the input x and examine them, we return the class that we saw the most among the k examples. So this is no different. So KN and logistic regression decision trees were quite easy to adapt. Support vector machines are not necessarily as easy. So there is a bit of problem here. So as you saw, some algorithms are easier to adapt, some are not. But as a general question, what should you do if you have a multi-class problem but a binary classification learning algorithm? And this you can apply to any classification algorithm basically. One common strategy is called one versus the rest. And the idea is simple. It is like to transform the multi-class problem into, let's say we have n classes. So rather than having one single algorithm for multi-class classification, it is like transforming the problem into n binary classification problem and then build n binary classifiers. For example, if we have three classes, 1, 2, 3, we create copies of the original data set and then modify them. In the first copy, we replace all labels not equal to 1 by 0. In the second copy, we replace all labels not equal to 2 by 0. In the third copy, all labels not equal to 3 by 0. And then we have three binary classification problem. And once we have the three models to classify the new input feature vector, we apply the three models on the input, we get three different prediction, and then we pick the prediction of a non-zero class, which is more certain. So this is you. So basically, the question is that does it belong to this class or any other classes? And by running that multiple times, we can get the accurate class. That was easy and intuitive, but what about one class classification? Sometimes we only have examples on one class, and we want to train a model that would distinguish examples of this class from everything else. One class classification tries to identify objects of a specific class among all objects by learning from a training set containing only the objects of that class. This is different and more difficult than the traditional classification problem, which tries to distinguish between two or more classes. A typical one-class classification problem is the classification of the traffic in a secure computer network as normal. In this scenario, there are few, if any, examples of the traffic under an attack or during an intrusion. However, the examples of normal traffic are often in abundance. One class classification learning algorithm then are used to outlier detection, anomaly detection, novelty detection. There are several one-class learning algorithms. One-class Gaussian, one-class K-means, one-class KNN, and one-class support vector machine. So this is one class classification. There is another one, In some situations, more than one label is appropriate to describe an example from the dataset. For example, here we talk about multi-label classification. In this image that you see here, we could assign several labels. It could be mountain, it could be road, it could be both of them at the same time. So if the number of possible values for label is high, but they are all of the same nature, like tags, we can transform each labeled example into several labeled examples, one per label. These new examples always have the same feature vector and only one label. That becomes a multi-class classification problem. And then we can solve it using one versus the rest strategy. The only difference with the usual multi-class problem is that now we have a new hyperparameter that is threshold. If the prediction score for some label is above the threshold, this label is predicted for the input feature vector. In this scenario, multiple label can be predicted for one feature vector. The value of the threshold is chosen using the validation set. Algorithms that naturally can be made multi-class can be applied to multi-label classification, like decision trees, logistic trees, neural networks, because they return the score for each class. That's why we can define the threshold and then assign multiple labels to one feature vector if the threshold is above some value. Neural network algorithms, for example, can naturally train multi-label classifications by using the binary cross entropy cost function. The output layer of the neural network in this case has one unit per label, and each unit of the output layer has a sigmoid activation function. And in cases where the number of possible value each label can take is small, we can convert multi-label into multi-class classification problem. For example, imagine the one that I have here in the picture. We want to label images, and label can be two types. It could be either photo or painting. And the label of the second type can have three possible values: portrait, paysage, and other. We can create a new fake class for each combination of the two original class. And now we have the same labeled examples, but we replace them with we replace real multiple labels with one fake one with values 1 to 6. This approach works well in practice when there are not too many possible combinations of classes. Otherwise, you need to use much more training data to compensate for an increased set of classes. And the primary advantage of this approach is that you keep your labels correlated, contrary to the previous one that we were using a threshold. Uh, and keep in mind that these correlations sometimes are essential. For example, if you want to predict whether an email is spam or not, and then you want to predict whether it's ordinary or priority, then you want to avoid predictions like a spam and priority. And so that was about problems or solutions. But before finishing this lecture, I also want to talk about something else. That is ensemble learning. The fundamental algorithms that we saw at the beginning of this course have their own limitations, if you remember. Because they are simple, sometimes they cannot produce a model accurate enough for the problem we are having in hand. We can try using deep neural network, of course, but in practice, deep neural networks require a significant amount of label data, which we probably don't have. Another approach to boost the performance of simple learning algorithms that we learned so far is ensemble learning. And ensemble learning is basically is a learning paradigm that, instead of trying to learn one super accurate model, focuses on training a large number of lower accuracy models and then combine the prediction given by those weak models to obtain a high accuracy meta model. Low accuracy models are usually run by weak learners, that is, learning algorithms that cannot learn complex models, and are typically fast. And one of the most frequently used examples is the decision trees, in which we often stop splitting the training set after just a few iterations. And if you remember, the obtained trains are shallow and not particularly accurate. But the idea behind ensemble learning is that if the trees are not identical and each tree is at least slightly better than the random guessing, then we can obtain high accuracy by combining a large number of such trees. To obtain the prediction for input X, the prediction of each weak model are combined using some sort of weighted voting, and then based on that we could get some more accurate outcome. There are two principles for ensemble learning methods: boosting and bagging. Boosting consists of using original training data and iteratively create multiple models by a weak learner. Each new model would be different from the previous one in the sense that the weak learner, by building each new model, tries to fix the error which previous models make. The final ensemble model is a certain combination of these multiple weak models built iteratively. Bagging consists of creating many copies of the training data. Of course, each copy is slightly different from the other one, and then apply the weak learner to each copy to obtain multiple weak models and then combine them all. A widely used and effective, it's actually very good machine learning algorithm based on the idea of bagging is random forest. A random forest uses a modified tree learning algorithm that inspects at each split in the learning process a random subset of the features. The reason for doing that is to avoid the correlation of the trees. If one or few features are very strong predictors of the target, these features will be selected to split examples in many trees. This would result in many correlated trees in our forest. Correlated predictors cannot help in improving the accuracy of prediction, and the main reason behind the better performance of model ensembling is that the models that are good will likely agree on the same prediction, while bad models will likely disagree on different ones. Correlation make bad models more likely to agree, which will basically kill the majority vote or the average. The most important hyperparameter to tune are the number of trees and the size of the random subset of the feature to consider at each split. Random forest is one of the most widely used ensemble learning algorithms. And why is it so effective? Because by using multiple samples of the original dataset, we kind of reduce the variance of the final model. Remember that low variance means low overfitting. Overfitting happens when the model tries to explain small variations in the dataset, because our dataset is just a sample, a small sample of the population of all possible examples. If we are unlucky with how our training set was sampled, then it could contain some undesirable, but of course unavoidable artifacts, noise, outlier, over or underrepresented represented examples. What we do in random forest is that by creating multiple random samples with replacement of our training set, we reduce the effect of these artifacts, and that is why random forests are so effective. And by that, I conclude the videos of this lecture. I wish you luck with your quiz this week, and see you next week.